Hello. In the last lecture, we have seen the definition of tangent vectors and definition of tangent spaces of a regular surface. In this lecture, we'll give the definition of differential map of a differentiable function from one regular surface to another regular surface. Okay, so then let us begin. Differential map between tangent spaces. Okay, so in order to define this differential map, what should you have first? So suppose you have a differentiable function from one regular surface to another. So phi be a differentiable map from the regular surface S1 to regular surface S2. So this S1, S2 are regular surfaces in R3. Okay. So now let us take a point. So let P belongs to, or let us take P1 belongs to S1, and let this P2 is equal to phi of P1. Okay. So now I'll define the differential of this map phi at the point P1. Okay. So suppose this is my surface and this is my point P1. So this is the surface S1. And I have a map phi from this S1 to S2. So this P2 is equal to phi of P1. Okay, so now, so what is the tangent vector at the point P1? So you take any differentiable curve passing through the point P1 on this surface S1 and take the velocity vector at the point P1 of that curve. Okay, so you take this curve. So suppose this is my alpha. So alpha of 0 is equal to P1 and you take this tangent vector of this alpha at the point 0. Okay, so this is my tangent vector alpha prime 0. So now, so alpha, it is a map in S1. So I can compose this with phi. So I'll get a map. So this is my phi compose alpha. Another curve, phi compose alpha. So this phi compose alpha, it passes through P2. So phi of alpha 0 is equal to P2. And you take this tangent vector, this phi compose alpha prime 0. So this is my tangent vector. So this vector is phi compose alpha prime 0. Okay. So that is my definition of differential of this phi. Okay. So the differential d phi at the point P1 from the tangent space of S1 to tangent space of S2 at the point P2 is defined as follows. So alpha prime 0, it belongs to T P1 S1. Okay, where this alpha is a differentiable curve such that alpha of 0 is equal to P. Okay, so this T phi P1 of this alpha prime 0 by definition, so this is my definition of d phi P1. So this is derivative of this phi compose alpha at the point 0. Okay, so this is my definition of this differential. Yeah. So this, note that this differential, it is a map from this tangent space of this S1 to tangent space of S2. So TPI SI uh, denotes the tangent space of SI at the point Pi. Okay, so we have defined the differential of a differentiable map. Now we'll check that. So this map is a linear map. So d phi P1 is a linear map. Okay. So how to check this thing? So again, let me draw a picture. So suppose this is my surface S1 and this is the point P1 and phi is this map, and I have this surface S2, P2 is this point. So phi of P1 is equal to P2. Okay, so now I can have surface patches in this following way. So I can have this U1 and open set in R2. So this is my R2, and I can get hold of a point Q1 here, and the sigma 1, it is a differentiable map from this U1 to this R3, where the image, it lies in the surface S1. So this is my sigma 1 E1. So E1 comma sigma 1, it is a surface patch, and similarly for this P2 also I'll get a surface patch. Okay, so I can also arrange this surface patch. So U2, so U2 comma sigma 2 is a surface patch. So I can get hold of a surface patch U2 comma sigma 2 such that this, so phi of sigma 1 U1 is contained in sigma 2 U2. Okay, so let me write down. So there exist surface patches ui sigma I such that so this pi is contained in sigma I ui, qi is contained in ui, sigma I of qi is equal to pi, and so phi of sigma 1 u1 is contained in sigma 2 u2. Okay, so here this I is equal to 1 to 2. Okay, so these are my surface patches. So ui sigma I surface patches. So this will imply that so this sigma I, it is differentiable, and the differential at the point qi, the differential of sigma I at the point qi is injective, okay, uh, for I equals to 1 and 2. Okay, so this T sigma I qi, it is a map from this R2 to uh, this R3. So the image it will be, so this injective map, so the image it will be the tangent space. So yeah, so maybe I'll just write this thing. So T sigma I qi of R2 is equal to the tangent space. Okay, so therefore, so therefore, so this map is a linear map from R2 to the tangent space. So this is an isomorphism. Okay, so this is an isomorphism. So therefore, so this is an isomorphism. So therefore, uh, inverse of each of these differential exist. Okay, so now we have this thing here. Okay, so now note that so from U1 to U2, I have another map, so which is nothing but equal to uh, sigma 2 inverse compose phi compose sigma 1. Okay, so this U1 and U2, so these are my subsets in R2. So U2, it is a subset of this R2. So I have a map from this U1 to U2. So this map is also a differentiable map from R2 to R2. So let us take, so let F to be equal to sigma 2 compose phi compose sigma 1. Okay, so then, so F is differentiable, okay, and T uh, differential of F, it makes sense. So differential of F at Q1 is a linear map. Okay, and so from this diagram, so it is clear that so this differential at the point Q1, it is equal to T sigma 2 at the point Q2. Inverse of this, compose D of phi at the point P1, compose D sigma 1 at the point Q1. So I have this thing. So from here, so D of phi at the point P1, so this is equal to T sigma 2 at the point Q1, compose df at the point Q1, compose T sigma 1 at the point Q1 and inverse of it. So I have this thing here. So the right hand side here, so this is a linear map. It is a composition of linear map. So this is a linear map. So this implies that so d phi restricted to P1 is a linear map. Okay. So this is a linear map. So that is the thing we want to show. Okay. So now let us give some examples. So let us take any regular surface in R3. So let S be a regular surface in R3, and let us take a unit vector and B belongs to R3 be a unit vector. So height function with respect to B is, so this already we have defined earlier. So this is what? So this is a map. So from so HB, it is a map from this S to R. It's a real valued map. So HB of this P is equal to this dot product, P dot product with P. So this is my definition of the height function with respect to the unit vector P. Okay. So this height function, this is a differentiable map. And now let us find the differential of this height function HB. Okay. So DHB at the point P, it will be a map from the tangent space of S to the tangent space of R at the point HBP. So tangent space of R at any point, again it is equal to R. So DHB P is a linear map from the tangent space of S to R. Okay, so how to compute this differential? So let us take, so let W belongs to TPS. So then, so there exists a differentiable curve alpha defined on minus epsilon to S such that alpha 0 is equal to P and W is equal to alpha prime 0. Okay. Okay. Uh, so then, so what is my DHB at the point P of this alpha prime 0? So this by definition, so this is HB compose alpha prime 0. Okay. So we have to compute this thing. Okay, all right. So now, so what will be this? So this will be equal to, so limit t tends to 0. So hp of alpha t minus hp alpha 0 divided by t. Okay. So this is again limit t tends to 0. So by definition hp alpha t, it is nothing but p dot alpha t minus p dot alpha 0 divided by t. So which is again equal to limit t tends to 0 p dot product with alpha t minus alpha 0. So this t you can take inside. So we have p dot product with alpha prime 0. Okay. So again, which is nothing but p dot product with w. So therefore, the differential of this hp at the point p of this w, it is nothing but p dot product with w. Okay, so this is one example. Let us do one more example. So let us take the sphere. So let S2 be this unit sphere. So this is a regular surface in R3. And now we take a rotation by an angle theta about the z-axis. So let r theta of xyz is equal to this thing. So cos theta sin theta 0 minus sin theta cos theta 0 0 0 1 applied on this xy z. Okay, so this r theta is rotation by an angle theta about z-axis. Okay, and so note that this r theta is also a linear map. Okay, so now how to find the differential of this map? So dr theta at the point xy z. Okay, so this evaluated at a tangent vectors, let us call it to be alpha prime 0. So this by definition, this will be r theta compose alpha prime 0. So this is by the definition. And again, so this is equal to limit t tends to 0 r theta alpha t minus r theta of alpha 0 divided by t. Okay, so here note that, so this r theta, it is a linear map. So because of that, so I can take this alpha t and alpha 0 inside this r theta. So r theta of alpha t minus alpha 0 is same as r theta of alpha t minus r theta of alpha 0, because this r theta is linear, and also I can take this t inside also. Okay, so therefore, so this will be equal to r theta, or let me do one more step here. So this is equal to limit t tends to 0. So r theta, by definition, it is this matrix multiplication. So a theta, then you have this vector. So where this a theta is this rotation matrix. So cos theta, sin theta, 0 minus sin theta, cos theta, 0, 0, 0, 1. Okay. So now I have, so this a theta, this a theta is this matrix multiplied with this vector alpha prime 0. Okay, so this is nothing but again equal to this r theta of alpha prime 0. Okay, so dr theta of alpha prime 0 is again equal to r theta of this alpha prime 0. Okay. Okay, so in fact, if I take any linear map, so observe that. So if t r3 to r3, or in fact, if I take, let us take r2 to r2, be a linear map. Okay, so then, so dt at the point xyz of any vector b is again equal to t of b. Okay, so this is very easy to check. And now let me give you the definition of local diffeomorphism. So a mapping, so phi from this open set U of S1 to S2, so where this U is an open set in S1 and this S1, S2 are regular surfaces in R3, is, so this map phi is said to be, so is said to be a local diffeomorphism at P belonging to U. So if, so there exists an open neighborhood B of P in U such that, so this phi restricted to B from, so phi restricted to B, it is a map from B to phi B, is a diffeomorphism onto an open set phi B of S2. Okay, so this is the meaning of local diffeomorphism. And as an application of inverse function theorem. So we have the following thing. So an application of inverse function theorem yields the following. So if S1, S2 are regular surfaces and phi is a differentiable map defined on an open subset U of S1 and so if S1 and S2 are regular surfaces and this phi is a differentiable map defined on an open subset U of S1 and so D of phi at the point P is an isomorphism for P belongs to U. So then, so this phi is a local diffeomorphism. Okay. So how to show this thing using inverse function theorem? So you just take this diagram. So suppose this map phi, it is given from an open subset of S1 to this S2. And I have this map, okay? And this, if I take the differential of this map, so this will be an isomorphism, and now you apply the inverse function theorem. So this will tell you that, so this map, sigma 2 inverse compose phi compose sigma 1, so this will be a local diffeomorphism, and that will imply that phi, it is a local diffeomorphism. Okay. All right. So I'll stop here. We'll continue in the next class.